Okay, let's keep talking about the first periodic like vibration model. Okay, and as you just figured it out, like in the particle solution, we have like the difference, different amount with the external force, right? Which was 1 over the square root of like k minus m gamma square plus b square gamma square. Okay, that part that we can define as like m gamma. That is exactly frequency gain or gain factor. Okay, so simply we can write your like particular solution. I mean, like frequency of particular solution as like f0 times m of gamma. Okay, we try to make a much simpler notation. Okay, so we're gonna say, like as you talked about it, um, like this is like difference, and we're gonna say like m gamma as the frequency response curve or resonance curve. Okay, so well, like later we're gonna talk about the detail of this one, but like let me like I would love to show you the like graph of that one. Okay, that is exactly the graph for the frequency response curve, which is resonant curve. Okay, and we will like keep talking about this when I derive to find like exact one. Okay, there we go. Let me come back. So here we go. But that's really like basic and easy to understand about the like motion of this. Okay, look at this one. Okay, we just try to find m prime. That's exactly what it is in section 3.7 to find like local extrema, right? And m prime, well, just like it is the like whenever you write your m as a negative power form, then do the derivative of your m function with respect to gamma, then you can easily find this guy, okay? Then now we're gonna try to find that equal to 0, okay? And you understand like why we try to find m prime equals 0, right? To find the critical numbers, okay? Because like critical numbers are the candidate for the local maximum, local minimum, okay? So to make this one, basically the first part, when your gamma equal to 0, then this fraction is equal to 0, right? There we go. I just state here, right? But not only this one, but also this part, okay? When your gamma is the square root of this part, which means square root of like, k over m minus b squared over 2m squared, then this one is also equal to 0, which means we have like two critical numbers, right? But think about it. If your system is overdamped or critically damped, okay? We talked about this before, right? Which means there's no maximum. Then your m prime gamma equal to 0 is only when like gamma equal to 0. I mean, like there's no other part, right? As I showed you like in the previous section, like, the spring is stretched. When you release, it just go back to the equilibrium position, okay? Which means there's no other like the local extrema, or like we can say like there's no oscillation, there's no vibration, right? And we are talking about that, okay? So overdamped or critical damped case, like there's no like a maximum, okay? Which means like there's only one critical value, which is gamma equals 0, okay? But it is more interesting about the underdamped motion, okay? When underdamped, we have another maximum at this point, right? And so we're gonna say like this value, gamma R is called the resonance frequency. So like if the system is stimulated by the external force with this frequency, and we're gonna say it is resonance, okay? So now let's talk about a little bit more detail about like this curve, okay? So like what does that mean? Whenever you have like a small damping, which is small b value, then like, you're gonna have like another maximum, which is the like a resonance frequency, okay? Like that point would be, there is resonance. But like, if you have like a really strong damping term, which means big B value, then like there's no more like, local maximum, okay? So now look at that. Like as I told you, like when B goes to 0, the maximum magnitude of frequency gain increased, okay? But what happened if there's no damping? okay? And we will talk about this one in next slide, okay?